Okay. Oops. Go back a bit. So the topic for today obviously has an awful lot of things in it. So it's not going to be deep dive on any of these things. I'm going to try and do a bit of an overview of sort of each of these topics. But before I get into it, I would like to say I love to be interrupted. Please ask questions, comment, whatever, or if you want to call me out on something I say wrong, that's good too. I think this will actually go better if it's a little bit more interactive rather than just me lecturing. So there's a fair bit. So we're going to talk a little bit about Linux, just generally, the command line in the shell, and then get into a bit of Docker and DevOps stuff, because of course that's all the rage, and it's one of the primary reasons why you might actually want to get to know how to use Linux and things in the first place. Like I say, kind of a mountain of information, but we'll truck through it. So Linux. Obviously, almost every operating system in the world has a similar sort of structure, at least if you look at it generically enough. And Linux is no different. Whether you're looking at Windows or Mac or Linux, basically there's a kernel of some sort that talks to the hardware, which supports system services and applications and things running in the environment. And Linux can do just about everything, right? It is a general purpose operating system. It's most often used as a server, but it can absolutely be a desktop. It's in IoT devices. It's probably in most of the Wi-Fi routers you've ever come across. And it's also very much present in things like routers and firewalls and network switches and other infrastructure equipment. So it's kind of a Swiss Army knife, which is nice. And again, one of the good reasons for getting to know a little bit more about it is just because so much of the world actually runs on Linux. Technically, being a little bit pedantic, Linux is actually only the kernel part. All the rest that tends to come bundled with your operating system, which is like system libraries and services, is actually from other projects, right? Linux specifically is the kernel. But of course, when most people talk about Linux, they're talking about, the whole stack, right? With services and everything else, something that's actually usable and is more than just a kernel. So, the more pedantic amongst the Linux geeks will say, well, no, you're supposed to refer to it as, GNU Linux or something like that, because that covers both system libraries and utilities and the kernel. But of course, nobody actually does that. People also often, when they're talking about Linux, they're actually talking about kind of an ecosystem. There's an enormous open source ecosystem all around Linux. There's a zillion different kinds of Linux desktops, Linux servers. It's been packaged a gajillion different ways for different reasons. And because it's open source and it's contributed to by people all over the world, there's just a phenomenal amount of flexibility in terms of what you can do with it. And an incredible adoption rate. Like I say, most of the IT world actually runs on Linux these days. That may not have been true 10 or 15 years ago, but now everything from the infrastructure that runs underneath giant clouds like Amazon, AWS, or even Azure, right? Even Microsoft's own cloud mostly runs on Linux, even if the workloads are Windows. And then, like I say, it's found all over the place in critical infrastructure, networking, and so on and so forth. Part of the reason, I think, for all of that success and all that flexibility is the fact that it's open source, right? So right from the beginning, it's been shared freely and widely. Anyone can contribute to it. Obviously, a large number of companies have formed around Linux and doing things with Linux. Red Hat could be one of them. Canonical, which creates Ubuntu, is another. And obviously companies like HP and IBM and so on contribute an awful lot to the Linux ecosystem as well. And basically everyone benefits from it, right? It's become this Swiss Army knife of flexibility and utility because so many people have contributed it and used it for so many different purposes. And there's a rich history behind it too. So Linux itself is not technically Unix, but it borrows an incredible amount from Unix heritage. So this image is a little hard to see probably on this screen, but that date at the top is 1969. And that's when the Unix story kind of starts. And obviously there's quite a family tree here. Pretty much all of the ones starting in the mid 80s and beyond I've actually used. But of course, Linux is the thing that we use the most every day. If you look at the family tree here, you see that there's actually no direct line from Unix ancestry directly to Linux, but it is considered part of the Unix family, even though it was a fresh start. And that is because it followed most of the same standards and patterns that had been used in Unix all through the years. And because of that, it inherited this incredible part of the previous ecosystem that existed in terms of all the commands and software and things like that that were available for it. You see other Unixes in there, right? Technically Mac OS is a Unix. And then there's a bunch of other, all the stuff in pink here is actually open source. So there are a number of other operating systems, not as well known, but they sort of share the same heritage and a lot of the same utility. So again, there's just in terms of standing on the shoulders of giants, Linux definitely does that. There's a massive amount of momentum stretching back over many decades into Linux, which again contributes to its utility and its success. So what can you use it for? Everything, of course. Desktops large and small. One of the nice things about Linux is you can, because there are so many different ways it has been packaged and wrapped up, it tends to be very useful, even on old and crappy hardware that can't run, Windows 10 or 11 and that kind of thing. It runs very well on virtual machines. It runs on all kinds of home entertainment equipment. It can serve almost any purpose in terms of serving up applications and things like that. And then, as I said before, it's all over the place in cloud infrastructure and networking, embedded devices. Your TV probably runs Linux. It's basically been squeezed into everything. It's also been blown up into really large systems. IBM runs it on mainframes, for example. So it runs the gamut. And an awful lot of software development and build infrastructure runs on Linux as well, which we'll talk a little bit more about that when we talk about DevOps and things like that. But a big part of the modern development ecosystem involving containers and whatnot comes from Linux, right? It started there. Well, technically it didn't start there, but it exploded in popularity on the Linux platform. And so a lot of the programming environments we use, a lot of the continuous integration and automation environments we use are based on Linux as well. Because Linux is primarily a kernel, and the thing you actually install is what we refer to as a distribution or distro. And it is a bundling of the kernel with the critical utilities and then a bunch of other stuff that whoever bothers to package the thing together decided were worth having, right? Obviously, there's a lot of commonality when you're talking about a desktop version of Linux in terms of what's available and so on. There are dozens and dozens of distributions, and you can actually go to a site called DistroWatch, which tracks the popularity of each and tells you what each of them is about and what they specialize in. And there are a really good set of starter user-friendly ones to kick around if you're interested in having a native Linux environment, right? And so I've listed a few of these here. I've actually got a bunch of them running here on my desktop, so we can kick some of them around if you want. Obviously, Ubuntu, most people have heard of. Linux Mint, which is based on Ubuntu, but is a little bit lighter weight and a little bit more approachable for people coming from the Windows 7 world. Fedora, which I use. Elementary, which some people claim is the most beautiful Linux desktop in terms of user experience and so forth. I don't buy that myself, but hey, it looks pretty nice. So, and then Pop! OS, which is actually a relatively new one. It's created by a company called System 76, who builds Linux laptops exclusively for Linux. It's also based on Ubuntu, but it has a very unusual interface. And so that's kind of fun. Any one of these is really good to a starter version of Linux to get into and to kick around. And they all look slightly different. I will take a quick pop out. For example, this is Ubuntu. Probably familiar to most people who have ever sort of installed a virtual machine with Ubuntu in it, or with Linux in it, because it seems to be the go-to thing. And this one, where's the other one? This one is Mint, which again, like I say, this is kind of a friendly environment to get into for people who are coming from Windows. It has that same sort of layout as Windows 7 and previous all had in terms of the start menu. It even has a control panel that's vaguely reminiscent of old school Windows control panels and things like that. So this is a very approachable. And I should say that almost all of these can be installed on a laptop or something like that with minimal intervention. In days gone by, you had a hard time getting a Linux system to work without jumping to the command line, doing a bunch of arcane incantations and things like that to make it work. But these days, it's really not necessary. Everything, for the most part, everything just works. Now, the shell. So because Linux has this history that comes from days of old, even before there were graphical environments, a lot can be done on the command line, right? It has a rich and powerful set of utilities. It has interactive shells or command lines, which are basically incredibly flexible. More recently, you've been able to get that with Windows PowerShell on a Windows system, but until that came along, the Windows command line really wasn't nearly as functional. It's intimidating often at first to get into the command line, just because there's so many commands to remember and things like that. But once you get used to it, it's incredibly powerful and flexible. It's sort of like going from an automatic to a stick shift, right? You gain a lot of control and a lot of utility from going to the command line. And obviously, when we get into containers and certain other development environments, you tend to have to drop to the command line, regardless of what operating system you're using. And so it helps to get used to the shell environment in these systems. And whether it's Linux or Mac, it's very similar. In fact, up until the most recent versions of Mac OS, they ran the Bash shell, which is the born-again shell, and that's the command processor for the terminal. I believe the new versions use something called Z shell or Z shell, depending on what country you're from, which is virtually the same thing. So, quick pop into a command shell. So, again, this is very similar to what you see on Macintosh as well, but when you open up the terminal, you get the command prompt, and then you have to figure out where to go from there. And of course, there are a whole handful of utilities built in to help you navigate, right? So you can list files with ls. A lot of these commands, again, because they come from really old systems where everybody economized on space and time, a lot of commands are like 2 or 3 letters. And so maybe that takes a little bit of getting used to as well. There's a directory hierarchy in Linux as well. It doesn't have drive letters like Windows does. It has a single sort of structure like Mac OS does. And so getting around is a matter of remembering a whole bunch of little commands. So ls is one of them. pwd, print working directory. Where am I right now? These kinds of things. And yet it takes, like I say, a little getting used to, but once you sort of know the handful of short commands and things like that, you can find your way around quite readily. And change directory, obviously, right? CD for change directory. most in a desktop environment, of course, most of the things you need to do in terms of plug in a USB stick and read files off, stuff like that, you can do with the old file manager, right? And that's friendly and basic. But when it comes into sometimes running new processes, occasionally compiling code, things like that, you will end up in the terminal. And we're going to play a little bit more in here again when we get to talking about Docker and stuff. Now, I am going to pause because I've been talking for far too long. Any questions about Linux? Anything you ever wanted to know and were afraid to ask? Speak up.
What is GNU?
GNU. It's one of these. It's a recursive acronym. It stands for GNU is not Unix. And it was created as part of free the initial free software foundation. And it's a collection of software, all licensed, generally speaking, under the GPL, which is the GNU public license, which is a license that says this stuff is free and open as long as you maintain it as free and open. So anything you contribute to the source code or any changes you make have to be contributed back to the source project. And some people view that as kind of a political license, and in a way they're right. It does have an agenda, and the agenda is that all software should be open source and free. And that is the license under which a lot of the software that runs in a Linux system is licensed. It's the license the kernel uses or did use originally. And it's meant to promote share and share alike, basically, in the open source world. The foundation that backs GNU, the Free Software Foundation, actually hosted and created the original versions of most of the system utilities you find in Linux. So when I'm poking around and I'm doing an LS and a CD and all those kinds of things, some of them are built into the shell, some of them are built into the system, and most of them come from the GNU project. And that's why those who are being pedantic say you should actually refer to it as GNU Linux, because what it is it's the GNU software system running on a Linux kernel, if that helps.
It did. What is bash?
Bash. So the command line prompt, in any Unix system you pop into, has a command processor called a shell. And it is the thing that interprets the commands you write and decides whether or not you're asking the shell itself to do something or you're invoking an external program. Bash stands for Born Again Shell, named after somebody called Born. There have been dozens and dozens of these shell processor environments over the years. Bash is derived from one called KSH, which is the corn shell. And it started with that origin and then enhanced it and added a whole bunch of its own sugar and syntax. The shells in Unix are actually really powerful because they're not just simple command prompts. They've got their own interpretive language completely. So you can do basically almost anything you can do in any software programming language, you can do in a shell environment. And that has been a massive utility, obviously, for system administrators in terms of automating things. Right. So for example, let's go back here. And if we go into our friend Meal Planner and we look at the startup script for the back end, start postgraph file, you can see this is the structure of a shell script, right? So the first line tells you which shell interpreter you want to run. Export creates a global variable, right? Sleep does literally that, goes to sleep for 5 seconds. And then we're invoking commands and we're running if-else statements right here, right? So you've got an if-else with the different tests. So this is saying if the number of command line arguments is not 0, or if this file exists, then run the database reset routine, right? And then, excuse me. And then a for loop, right? So for basically all the SQL files in start.sql do a thing, right? So shell shell is actually really powerful processing language as well as just a thing that it takes the commands you enter. All right. Anything else before I keep going?
So if I run that on my machine, which is the default is the Z shell, basically that doesn't mess up because the top of the file is saying this is bash or use the bash shell.
That's right.
Okay.
So it's the magic start to a text file. When you start with the pound or hash line and then the exclamation mark, then what follows is the command interpreter, right? So any text-based scripting language can follow that convention. So that includes Python and Perl and other interpreted languages like that that are basically run directly from the text form. Will follow that convention. It's basically telling the command shell that you are running which program is to be used to interpret the set of instructions that are in the file.
Makes sense. Thank you.
Yep. Okay, so a couple other points about, oops, a second, about that. A couple of nice things that almost all shells have as a feature. First is history. So I can using my cursor keys, I can scroll back through the history of commands I've run and re-execute them. I can also use the command history to list all the commands I've ever run. And then I could rerun them like so, exclamation mark and the number, and boom, and it redoes the command. So there's a fairly powerful history system. I don't think this is a big surprise to anybody if you've used a Macintosh terminal or PowerShell in Windows. You've got the same sort of thing. But it's immensely useful. Command completion also, if I, for example, hit tab a couple times and I'm trying to type a command, it'll suggest to me which ones are available with that prefix, and then I can pick the one I want. It also does this for files, which you can see when I was trying to edit the start postgraph file, right? It completes the directory name, and it completes the file name. So that's mightily convenient when you're trying to get a lot of work done really quickly, and or you can't remember exactly where you put a file. We talked a bit about the programming features. Another thing that's really powerful in shells is redirection and piping. And what that means is, let's talk about this command. So it's command cat, which will display the content of a file, right? So if I do cat license, it just dumps out the license file like that. But if I want to search for something in that file, I can pipe it. And what that means is instead of printing the output to the screen, it's going to print the output to the input of the next program I want to use. So I want to look for grep deal, right? I notice it picks out the line from the file that I was searching for. This is really powerful because what it lets you do is chain a whole bunch of commands together in one command line to get a compound set of work done, right? So the simple case is something like this, like searching. Another case, though, could be you're doing a really long-running processing. You're taking the output from that, you're feeding it into a subsequent program that's going to do something else. So a good case might be sorting, right? So if I want to I show a list of files. That's maybe not the best example, but I can pipe it into another utility called sort, right? And I can get that to show me, well, it's going to give me the same order because Linux is using alphabetical order automatically, right? But you can do a sort on the input. So obviously you can see if you're pulling a bunch of records from a database, for example, you could pipe them into a sort and change that. And so you can get these really long, fairly complex interactions all together in one command line. You can also take the output and redirect instead of piping to, oops, can't type today, so temp file, for example, right? And what that means is temp file now has the output of that previous command. So you can redirect output, you can redirect input, and in that way, really, just like I say, just chain together these huge workflows on the command line. And experienced system administrators use this obviously to great effect. But it's useful to get used to it when you're doing programming and stuff like that too, because occasionally you will want to compose a structure like this, or you want to do some automation, and the command line shell. The command shell is very helpful for that. All right. Containers. Second section of what we're going to talk about today. What is a container? Container is basically just process isolation. Obviously, there's nitty-gritty details in terms of exactly how it's done, but the idea is that you can take a process or set of processes and wall them off from the host system on which they are running. So that those processes basically don't have access to the entire system. They only have access to what you have decided is going to be inside that container. Right, so it's a slice of the system or an alternate view of the system. It has security properties, as you can imagine. If you run a process and you say this process can only see some small subset of what the host system has or what the user of the system would normally be able to see, then obviously it can not inflict damage on those other parts of the system. But containerization isn't really primarily for security. It has more to do with resource control, right? So by sticking something in a container, you can control, for example, how much the maximum amount of RAM it's able to use so that it can't exhaust the RAM in your system, or a maximum percent of CPU time that it can use so that it can't hog the CPU in your system. And then, of course, you can limit which files or parts of the file system on the computer that it can see. So it's a bit like a virtual machine, right? Except that a virtual machine emulates an entire other computer, right? It emulates the CPU, memory, hardware devices, everything all the way up. And within the virtual machine, you actually run a completely different kernel and operating system. Container isn't that. It runs on the exact same kernel in the host system. It's just a different view. It's a partition or slice of what the rest of the processes can see in the system. Very powerful, right? And I think we've seen some of it working on Meal Planner. You've gotten a bit of a peek at what Docker containers, for example, can do. This is not actually a new idea, even though it's an incredibly popular trend in development these days. Everything's getting containerized. It's actually a fairly old idea. It's just one that has come of age. And here's a bit about that history. So the very first thing that could be considered a container, if you stretch the definition a little bit, was actually back in 1979, again in the Unix world, where Unix version 7 introduced the change root command, or chroot. And that was limited to file system isolation. So when you use change root on a process, it makes that process believe that the top level of the file system is something other than it is. And so in that way, it can only see a subdirectory structure within the host system. Not really a container in the real sense of the word, though, in that it had nothing to do with limiting the amount of memory or process usage or even network access that process has. The FreeBSD jail came along many years later, around 2000. It's closer to the first container that actually limited process usage. It limited the program that's getting jailed has a limited view of the other processes in the system, limited memory use, things like that. This has started to evolve pretty quickly thereafter, right? Linux, there was a project called Linux vServer which was a lot like jails. It had process and memory containment, as well as file system containment. But it was never mainlined into the Linux kernel. It could only be used through a set of patches, meaning you had to compile your own sort of from scratch. So it never really became super popular, but it did have some use. And some hosting sites actually used it for virtual private server hosting and things like that. A few years later, Solaris containers. These were much more powerful. But of course, Solaris is really, I mean, it's still with us, but not really. It was very much like the BSD jails, but it also leveraged powerful features of the ZFS file system, which allowed for snapshots. So you could capture snapshots and things like that, which is got everybody a step closer to what we do today, where we have images that we can run in containers. And you could do that same sort of thing with Solaris containers. All of these older systems, though, involved a lot of command line calisthenics, right? The command structures were not simple. They were not obvious. They were hard to memorize, that kind of thing. OpenVZ made it a little bit easier. And in fact, that became fairly popular with VPS hosts. So in the early 2000s, if you had paid $10 a month for a virtual server from a provider like openhosting.com or something like that, chances are they were using OpenVZ to give you a virtual slice of an actual hardware system, and to limit how much CPU and memory you could consume. Things started to pick up pretty quickly at this point. So Google started the process containers. That never really took off on its own, but it became part of Linux control groups, which is an important thing for today's containers. Lxc Linux Containers was the first sort of native containerization, which sort of was baked right into the kernel and was available on all Linux systems. Wardens introduced an API, which was the beginning of actually having a modern container ecosystem. The big hit, though, was Docker. So when Docker came along, they produced a container runtime engine and command line tools that were really easy to use, or at least comparatively easy to use from what came before. And they just seemed to strike at the right time. It's a time when people were talking about decomposing systems, service-oriented architectures, and things like that. And Docker hit with this containerization structure, which was easy to use, easy to automate, relatively speaking. And so now we started talking about microservices, which is similar to service-oriented, but microservice adds extra elements to the structure, which tend to rely upon containers, right? Where you've got a bunch of independent pieces that comprise a larger application. And each of those pieces are contained and isolated, and they've got their own dependencies and libraries, and they don't interfere with one another. Container security, because people went a little bit too crazy with Docker and made a lot of assumptions about its security. Container security became a real issue, and that's when we started talking about integrating DevOps and DevSecOps into the way we use containers. We'll talk a little bit more about that. And it kind of complements Agile, which of course was also becoming very popular at the same time. So just the same way as we were thinking about decomposing our applications into a bunch of little containerized services, we're also thinking about decomposing our development cycles into short little iterations. And the two things complement each other quite well, which is why the other architectures built on top of containers, like Kubernetes, have also exploded in recent years. Running a bunch of independent little containers using something like Docker is great, but you really need orchestration, right? Because if you look, for example, that's a very small example, but if you look at our own meal planner application, it actually runs in 3 independent containers. And they all have to know how to talk to each other. They have to know how to find each other. And that kind of thing. And so if you get a bunch of people on the command line stitching together Docker containers one at a time, that doesn't scale very well. What you need is orchestration, something that's very declarative that says, okay, I know I have 3 containers and I know what each one of them is. I want to give them a name. I want to tell them how to talk to each other. And I want to be able to hit a button and have it all go. right? Kubernetes is a very mature expression of that whole idea. It is a full-blown orchestration system that allows you to distribute containers all over the place. It handles availability and everything else. And we'll talk a little bit more about that in a bit. But in 2017, Kubernetes, which had started at Google, sort of hit a maturity level where it was usable by a wide range of development projects. And so it accelerated rapidly. And it's one of the main reasons why we're all talking about containers now, today, in cloud development and things like that. Is because Kubernetes is just incredibly powerful and very mature. That adoption increased, of course. There's the Cloud Native Computing Foundation, which is kind of an industry group that organizes all the parts of the Kubernetes and cloud ecosystem, and sort of helps with standards and certifications and things like that to make it all work well together. And a lot of this is digital transformation that people are talking about, the move to cloud and hybrid cloud and everything else like that. A lot of that is contingent upon using something like Kubernetes. And then 2019 was a banner year. Again, it took things a little step further. So again, with some other projects that sort of came into their own maturity-wise, where you had full stack orchestration systems, which are based on Kubernetes, but then add their own layers and flavors on top of it to sort of enrich it, make it more approachable, to add user interfaces to it, things like that. So IBM's own Cloud Paks, as well as Google Anthos and AWS Outposts, they're all sort of playing in that space of layering services and utility on top of Kubernetes. And Red Hat's OpenShift is a big part of that. So anyway, that's a little bit of how we got here. It's actually been a really long journey, but it has picked up speed massively in the last few years. Using Docker. So let's pop out here again. And again, I will use Mirror Planner as an example because it's something we can relate to. It does use Docker, and so basically, the basic features of Docker in order to make things happen. But I'll just demonstrate the basic usage of Docker and how it works. So because a container has its own little slice of a file system, right? So it only sees the file structure that you give it. What you need to do is create those little file structures that will then end up in the container so that the Docker so that whatever processes are running inside your container have something to work with. And these are images. So you can start your own from scratch, create your own little, stitch together your own little file system from bits and pieces all the way up. But of course, that's not practical. So generally speaking, what we do is we go to pre-built images out there in the world, and they are in registries. And registries are really just versioned collections of these images that have been built, typically by somebody or a company or potentially just by developers who are working on the project. And we actually do this all the time. So when you're in Mirror Planner and you do the Docker Compose thing to start it all up, you're actually building images and you're storing them in effectively your local registry. So let me demonstrate that. So if I do Docker image ls, right? So Docker subcommand is image. I want to see what images are on the system. I do a list. And you can see that I've got Mirror Planner, the three components of Mirror Planner, and I've got a Postgres, right? Because our backend database is Postgres. There's also a couple node images. Now, we don't run those directly, but the Mirror Planner images are based on node. And so these images show up here in the repository as a dependency of that. And I'll show a little bit more about how that works in a second. So if I wanted to, for example, I was inspired by Vladimi's presentation of last week, and I wanted to look at, I want to play around with Postgres. I can literally just run interactive Postgres, and then I say, I want to run my shell so that I can poke around in the system. Done. So I've just started a container based on the Postgres image. And now it's up and running, and the command prompt changed. as you can see right here. And this means that I'm actually inside the container. So my view of this entire operating system now has been, is not even there. It doesn't even have PS, right? So it doesn't even have to have half the commands I need to run things, right? But it does have its own file system. And I can connect to, I should be able to connect to Postgres. It's not initialized yet, so we can't do that, right? So I have a very, very restricted view of the world here, right? This container has basically only the stuff in it that it needs to run Postgres. I can't see if I list, for example, the home directories, right? There's no users in the system or anything like that. So I've got this restricted view of the file system. I wonder if I can, no, it's not there either.
Are those files and folders shared with the host system, or are they entirely contained within the container?
They can be viewed from the host system. Because again, the container is actually a slice of the host system. So what, in fact, what an image is that you download from the registry is really not that much more complicated than just a big zip file with all this stuff in it. And so what happens is when you run the container, it takes that zip file, it's a tar file actually, but whatever, it extracts it, and then it executes the container using that content as the new root directory for inside the container. And it does a bunch of other stuff as well, right? There's a bunch of things built into the kernel. The kernel has what's called namespacing. So where the old-fashioned, what I first referred to from the old days of Unix, where they implemented the change root command, change root would give you this file system namespacing effectively, where you would only get to see a small part of the file system when you're in that change root environment. Linux adds namespacing for all the other aspects of the system as well. So you can't see processes that are running outside of the container when you're inside the container, right? So even though your host system may be running other containers, maybe running thousands of processes, you can't see any of those. And that's because of namespacing. You're restricted to the namespace for your container. Networking also, there are network namespaces. You cannot see the network interfaces on the host system. You actually have your own virtual network interfaces inside the container. And so that combined with what Linux also calls control groups, the two things go together. Namespaces change what your view of the system is, and control groups control what you can do in the system, basically how much CPU you can use, how much memory you can use, and that kind of thing. So those all come together. And if you were to try and, in fact, if you look at the old Lxc version of containers, setting up a container was incredibly complicated because what administrators had to do was define all those control groups and namespaces and reference all of them and put it together themselves. Why Docker is so powerful is that it just does that for you, right? It has some basic opinions about the right way to use those features of the Linux system, and it does it for you. And it's very declarative, it's very predictable. And so that's how it's basically so easy. Like you saw, I just run the boom, I do the thing, and now I'm inside a container, right? And then as soon as I exit it, the process is terminated and the container is shut down. And how you can see that, if I do this, see, this is actually not the same Postgres I was running. So this is Postgres from the meal planner that I started up about 7 hours ago. It's still up and running. But if I do a Docker PS and I pass -A, which means show me everything, even the ones that are shut down, you can see that this is the one I was just running right here, right? And it finished, it exited. So the process exited, but that copy of the file system and everything else is actually still present on this, under this container ID, right? And should be able to restart that same container. Nope, it wants the image. Oh, sorry. forgetting my own commands here. Don't normally do this because I usually destroy containers and it's not there. So the container was still there, and I was able to restart it, and it used the same command line options as I had used when I ran it the first time. So it knows that I want to run a shell, a bash shell, because that's part of the definition of the container that's sitting right here. Right? And it's the same container that I was in before. So it's the exact same instance of the container. And usually the command prompt changes right here, so you can tell which one you're in. So you can pop in and out. You can restart the process with that same file system or whatever, or you can do a Docker RM for remove and trash it. And now if I do list all containers, it's gone completely. So now that little bit of file system and everything else is all cleaned up and gone. This is a little weird to wrap your head around when you first get into it, because it's like running processes, and it's also sort of like running virtual machines, but it's not really like either one of those things. So it takes a little getting used to. And because Docker, like I say, is kind of an opinionated way of using containers, it takes a little time to get used to the Docker command line and its various options, right? So continuing the tour. So PS basically lists the containers, PS-A lists all containers, including the ones that are shut down. And then of course you can remove those and clean up. You can also have a look at the images, I did that before, that have been pulled down as part of previous executions of the thing. So you see the meal planner stuff there, and we'll play with those a little bit after. Let's say I want to do something completely different. I want something that looks like a Red Hat system. Oh, I can't do that with a log. Wait, I can do it this way. Actually, maybe I can't on this system because I don't have credentials. Maybe screw myself. A second. Let me see if I can make this work. Gotten so spoiled by using my work system that I'm not accustomed to limitations here. Oh, it won't work. So let me try this. Still can't do that. So I can't do a poll. Give me 1 second here, just to try and demonstrate this. I will do it on my other system. So in this terminal, where I have access to everything, I can do the Podman version of the same thing. Podman is an alternative to Docker. Try not to get too distracted by that. Oops. Ta-da. Now, what it's doing here is it's gone to the registry. It's looked up the image for UBI 8 minimal, which is a stripped down version of Red Hat Linux. And it has pulled down the image for it, right? And now if I do, you'll notice these are the same as the Docker commands. I can see I've got UBI 8 minimal, right? And so now I can Docker run -ti. I can run it based on the image ID, right? And I can do bin bash. Boom. And now I'm inside something that looks a little bit, let me see, that looks a little bit like Red Hat. Here we go. And I can check that. Red Hat Enterprise Linux. Boom, right? And that, but the system, the host system I'm running this on is actually not Red Hat. So again, this is a way I'm able to pull down an image that has all the Red Hat packaging and things like that in it. So if I want to test a piece of software, let's see if it works on Red Hat, I could do this interactively really quickly. So, now, when you create the container, whether it's from using a Docker run or from using a compose, which we'll talk about in a minute, like I said, it creates this little snippet of a file system, and you can actually see what those are on your system, right? So these are volume names. Most of these are really difficult to attribute to a container because they've been randomly named. But you'll notice that one of them has been specifically named, and this is the one that goes in my Postgres database container. So when it was created by Docker Compose, it was given that label. If you look at we'll get more to Docker Compose in a second, but if you look at that, that is basically from here, which is why it's got Meal Planner PG data. Meal Planner is the project, PG data is the volume name. So the volumes are on the system here, images are on the system, and containers on the system. And those are the things you're playing with all the time when you're running containers, managing containers, building containers. Is the images that you've based it on, based your work on, and then the containers and the volumes that go with those containers. There's a bunch of other magic that Docker's doing behind the scenes. It's actually playing with network namespaces and everything else inside of Linux. For the most part, you don't care. You don't need to. Now, one more little trick before we get into how you build your own image. This Postgres container is still executing, right? I started it 7 hours ago. Its current status is up, and it's been up for at least 6 hours. And it's actually at the back end for the Meal Planner. If I was trying to troubleshoot something, that process is not working right, or it's a config file that's wrong, or something like that, I can actually intrude using exec instead of run. I can actually intrude into this, and I can use it by container name, or I can do it by label. Oops. There. So now I'm inside the already running container, and I can see what the environment and things like that are, right? This is from the env file in our Meal Planner project, things like that. So I can have a look at the environment. I can poke around and maybe get a look at what might be going wrong in the container that I created if it's not behaving correctly, right? So in addition to running it, I can actually intrude into the namespace of a particular container by using exec. And that's one of the ways in which it is this kind of fuzzy gray area between a virtual machine and just another process. Because it's inside the container, it's got its own isolated environment and everything else. The content of that container is very focused on a single purpose. And so I'm not going in and debugging an entire server trying to figure out what's going on. I'm looking specifically at the properties that belong to that container and why they might be goofy, for example. So Docker pull, Docker run, Docker exec, image ls. This is how you're navigating in your environment. Now, let's suppose you want to build an app based on Node, which we do, but you need more than what's available in the stock container out of the registry. You want to build a new image that has everything that Node has, but also your own code and your own utilities. For that, you use Docker build. And Docker build takes a set of directives from something called a Docker file, which describes exactly how to do the build and add the tools and utilities you need. So let's have a quick look, again, using Meal Planner, since it's right here, at Meal Planners. So the front end has its own Docker file, right? And it's real simple. when you do a Docker build, it reads this file. The first line is always a from. The from is the image you're going to start with. In this case, we're starting with node version 12. And node :12 is exactly what you would write on the Docker command line if you're going to do a pull. You Docker pull node :12, and it'll go to a registry and try and find node version 12 and pull it down for you. This specifies within the container a working directory that all the subsequent commands are going to use, right? So this is sort of like change directory on the command line or CD when you change it to a directory. This just sets that as, okay, I'm now in /app, and all the other stuff I'm talking about is going to happen in /app. What's important to know is that all the commands that happen from here on create a new layer. And this is the way images are built. So the image has, like I said, this sort of zipped up little file system that has all the things you need for Node, including a subset of the file system from a full operating system. And when you do a copy or a run or one of these other commands, what it's doing is it's creating a new, very small overlay zip file with only the things you're adding to it. And it creates what's called a layer. So underneath the image that you're about to build, you literally have the original zip or tar from Node, and then a smaller one that has just the little bits that you added into it. And this is the way that the images are composed, and they're composed in layers. And that allows for a lot of flexibility in your local registry, right? For example, when we looked at the Docker image class, you notice that Node is in here, and it's because it's a dependency of these guys. So what these are, they have their own image ID, but they make instead of storing all the stuff from the original Node image, what they do is they store a reference to the Node image that it came from. And so if you were to publish Meal Planner front end to a public registry out there in the world, and there's a ton of them. There's Docker Hub, GitHub now has its own registry. All the cloud platforms have their own image registries where you can put your images so they can later be pulled by somebody else. So if you were to take Meal Planner front end, put it in one of those registries, it would implicitly push that one up as well. So if this image was not already in that registry, it would go push it up into that registry as a dependency. So that way, your Meal Planner front end doesn't have to be this massive, huge thing, although it is actually pretty big because it's Node, right? But instead of being 1.2 plus a whole other gig, it's only 1.2 gig. And so as you add on these layers, building up a Docker file, you're adding smaller and smaller little bits. And that's economizes on space. It allows for upgrading of base images without messing with the layers that you have and things like that. So it's important to know that, partly to try and economize on exactly how many commands you put in a Docker config file, because you could be creating a massive dependency tree. And oftentimes it's worth starting, if you need things that aren't in a particular base image, it's worth starting with a richer base image so you don't create too many extra layers. But it's a balancing act. Anyway, so copy now, we'll copy the content from the current directory. That's the one that the Docker file is in, into the working directory, which in this case is /app inside the container. So in the case of Meal Planner, what that's doing is taking all your Node files, right? The package lock and the Node modules and everything else that are in the Meal Planner UI directory, and copying them into this container image, and then running npm install, right, to actually update all the modules in Node modules. So this is what you would do on the command line if you were using Node and you were just checking things out of Git and running npm directly on the command line. Same idea. We're doing this here, but we're doing it inside the image, so it will be captured as part of the built image. And then we say, okay, we're going to expose port 3000. That's the port that our thing listens to. And then Docker will use that to when it comes to port mapping and setting up network namespacing. and then command, which is also called the entry point. This is what happens when you actually turn this thing into a container by doing a Docker run. What's it going to do? It's going to run this command. So pretty simple, actually. What you've done is you started from a node base image. You've installed the Meal Planner UI with all its dependencies, and you've wrapped that up in an image, and it's now available to be run directly, right? So I can actually run that. I can go Docker run Meal Planner front end. Bash. Oops, Bash doesn't exist. There we go. So see, it's dropped me into /app because I specified that as a working directory in my Docker build file. If you look in here, it's got the content for the Meal Planner UI, right? This is not the actual Meal Planner UI. This is a copy of it that's inside the container image. So now I've got everything I need to actually run the front end. Problem is, this is a multi-container application. So the front end needs to know how to talk to the middleware, the GraphQL, which in turn needs to know how to talk to the database. There's nothing inside this container that tells me where my GraphQL server is. And this is why, as I mentioned before, you actually need orchestration for multi-container services, right? So let's, for a second, pop back to the slide. So this is what I was talking about here, right? So images live in repositories, and they're sort of an implicit local repository on your own system when you're building things. You can take those images and run them. And when you run an image, it becomes a container. And that's the distinction between the two. The image is the stock dead thing that sits in a registry. The container is the thing that's actually executed and has a defined namespace and constraints around it. Image is not much more than a file system. You can build an image using Docker files and commands in Docker files that creates new layers, right, which end up in your repository. But now we want multiple containers to talk to each other. And so we need something to orchestrate all that, to tell them how to find each other and hook it all up and make sure the networking works and everything like that. And that's what even richer orchestration systems like Kubernetes and everything are about. But a simple one that comes with Docker is Docker Compose. And again, we do use this in Meal Planner, as I'm sure many of you know and you've seen. So let's have a look. What Docker Compose does, sorry, one sec, list the files here. What Docker Compose does is it reads a definition from a configuration file, which is expressed in a language called YAML, which is a really simple syntax used for defining configuration. And what this orchestration does is it implements what we call a declarative configuration. So it declares the state we would like things to be in, and then the orchestration layer makes that happen. So the Docker Compose is a really simple version of this in that we define in this compose file the way we would like things to run and interconnect. And then when you run the Docker Compose command line, it tries to make all that happen for you, right? There's a pile of documentation on docker.io about how to use Docker Compose and everything else. But this is actually a pretty good example of the one we have in Meal Planner because it's a three-part compose. And so it actually shows how the compose orchestration stitches everything together. So we'll run through this real quick. Start with the version. I don't remember what the current version is. It's beyond 3.7, but that's okay. That just helps define specific syntax for each of the things that are in it. Services. Services actually refers to the set of containers that we want to run. Next level down, we actually name the containers. So you see there's DB here, GraphQL here, and then finally front end here. So, and this is part of the YAML syntax, right? Everything's indented. Syntax is really simple. So there's a hierarchy to it, just simply using white space indents. So for the DB container, we define the start image, right? Which image are we going to pull from our repository to run? Restart refers to what happens if it dies or crashes, compose will restart it. Which ports are going to be exposed to the world from this container? So what we're saying is on our host system, if we connect to port 5433 on localhost or whatever, it will actually map that to port 5432 inside the container. Now port 5432 is the Postgres port inside the container. So, and ports, by the way, means TCP ports. Volumes, this is where we have this named volume, right? So we say, so from the Docker environment, we're going to use a volume called PG data, and inside the container, we're going to map it to this location, which is where Postgres expects its database to be. We do this so that we actually persist the Postgres, right? Because remember, a container, when it stops or it's removed, its data is gone, trash, right? So we use volumes to add persistence to containers. Right? Because normally, if you create no volumes whatsoever for a container and you run it and then you exit and shut down, any changes you made to the files during that runtime are gone, right? The container definition, once it's shut down, is nothing more than what was in the original image. This allows us to expose extra file systems and have them persisted so that when you shut down the container, the Postgres data remains. The next time you start up this Postgres container, the old data is still there, right? So you still have your meals and meal plans and everything else. So that's an important feature of an orchestration system. And of course, this gets even more complicated when we talk about Kubernetes. Environment, again, these are the configuration variables that are loaded into memory in the thing. In this particular case, we're saying we're going to read it from the .env file, which has a Postgres password that we want to use and things like that. Right? So that's a Postgres container. GraphQL, the DB image is slightly different from the others in that we're not actually doing an image build. We're just using Postgres the way it comes from the external repository, right? So we just say DB image and go to town. GraphQL, though, that's got our code in. So we need to do a build with the Docker file. And so we're going to say build, and we're going to say context. Context means in what directory, subdirectory from relative to this Docker compose file, can I find the Docker file that will build my GraphQL container? And that's in the backend subdirectory in the new client project, right? So this says, okay, Docker compose, when you start up, you need a backend container. And if it doesn't exist, you got to build it using the Docker file, right? And then expose the ports, port 4000, right? That's our GraphQL port. Now, volumes are a little bit different in this case. What we're doing is we're saying take it to the local project directory, backend, which is where all the GraphQL stuff is when we check out our Git project, and mount it or map it to /app in the container. Now, this does something interesting for us when we're doing development, because you notice when we build a container, we created an app and it had a copy of the project files from backend or front end, depending which container you're building, or sorry, which image you're building. But what we're doing this time is saying, okay, when you run it as part of the compose, forget all that, load up the local backend directory and map it to the /app inside the container. And what that does is it pokes a little hole in your container effectively, and it says, excuse me, /app in this instance of the container that I'm about to run is actually the host file system, right? So all that stuff I was saying about containment before, where the container can't see any part of the external host, you can violate that rule selectively. And that's what we're doing here. And the reason we're doing that is because we want things like hot loading and stuff like that. So if you go and change your JavaScript, right, on your desktop using Visual Studio Code or something like that, we don't want to have to go rebuild the container and go through all that build cycle just so that we can see a one-line change. We want it reflected immediately. And that's exactly what this volume mapping allows us to do. This one counteracts part of that. So it's kind of funny. So we wanted to expose the backend project so we could change our JavaScript and mess around with it. But this one says, by the way, mask the node modules, right? So node modules inside the container is its own copy of node modules. It's actually not the one that's in your local file system. And we do that by specifying this path without a colon and a mapping, right? So we're saying for node modules, take what was actually built in the original container instead of playing this trick where we're mapping the host file system. It's not strictly necessary. This was done just so that when you're messing with your dependencies, what's in the container is really what you're using at runtime. So that when you check in your code and you test it and everything else, you're working with sort of a constant or steady set of dependencies. And that just helps us, from straying too far from one another when we're actually doing our builds. All right, and again, if there's any extra environment, read it from the .env, but we actually declare the environment specifically. Now, a trick, and one reason why Docker Compose allows us to do this stitching together 3 containers so well, is that if you look at the Postgres URL, so we've got our password and stuff that comes from the environment, but it's using this hostname DB, which is not a real host name in the real world. But when Docker Compose starts up, it messes with all the networking and namespaces, including DNS. So when we refer to DB here, it's actually this. So if you run the GraphQL container and say you use Docker exec to go inside it, and you do a lookup on the hostname DB, it will actually point you to the internal IP address of this guy. And this is where the power of the orchestration starts to show itself, right? Docker Compose is stitching these things together for us by magically making DNS work where it wouldn't normally work and things like that. That's part of the power here, and this is one of the ways it reveals itself. Right, and same here, it's referring to the host name. Depends on. This is part of the Docker Compose dependency. So the Docker Compose knows that it can't start the GraphQL container until it has started the DB container, because GraphQL depends on it. And by the same token, links. So what that does is it tells Docker Compose that these have to continue running all the time together, right? It needs the DB in order to, it needs to be able to talk to the DB over the network, and it needs to be running. Okay. I'll try to burst through the rest of this because we're going to burn a pile of time here. So front end, similar idea. Context is where is the Docker file for the front end container. What ports is it going to use on the network? We map the local directory to make this useful for development. We mask out the modules directory, same as we did before, but in this case, we also map the backend to /backend. And we do that so that the GraphQL server can find the front end server can find the GraphQL schema file that is generated by the GraphQL container when it starts up. So again, we're taking the local host directory and we're making sure that it's mapped to a path inside the container so that the node front end running inside that container can find the schema file that's been generated, the most recent version of it. And then we tell it how to get to the actual GraphQL server, right? And specify that it depends on GraphQL, which means it has to start first before the front end can start, and it needs to be able to talk to it over the network. Admin interface, similar. Most of us aren't actually using the admin interface. Same idea though. It depends on the GraphQL, and it doesn't. It has a different build system, so there's fewer options here for the modules and things like that. And then we declare the volume, right? So we reference the volume at the top in the DB container called PG data. Here we're telling Docker Compose it actually needs to create a volume called PG data. Okay. So that was a quick run through, but you can see the orchestration is powerful, but also gets complicated quite quickly. Docker Compose is one of the simplest forms of that kind of orchestration. When you get into things like Kubernetes and so on, and other cloud native development systems, this orchestration gets even more complicated, which is why newer systems built on top of Kubernetes are really important, because they provide graphical interfaces to all this kind of stuff, and they allow you to build, deploy containers and stitch them up and do all the networking without necessarily having to write a lot of code or YAML. All right, I spent way more time on that than I thought I was going to. Any questions? Confusions, frustrations?
My brain is leaking.
Well, I tried to use the meal planner as the example because it's something we've at least all seen, right? And so even though there's a lot of complexity to this, at least it's a somewhat familiar reference.
You removed a lot of mystery, I won't lie.
Okay, that's a good thing. We'll take that. Allow me to move on, since we're probably running out of time here. Okay, so this is mostly talking instead of demonstration because I did not set up a Kubernetes cluster for the sake of going through this. We could spend hours and hours talking about Kubernetes. It's amazing and powerful and also frustrating and complex. But what it is a rich orchestration layer that doesn't just stitch 2 or 3 containers together. It manages entire clusters. It balances workloads across nodes. It makes absolutely certain that things are running. It provides routing and so on from the outside world into the cluster so that the outside world, the internet, can talk to your applications, for example. Highly available, could be highly distributed, and so on. So, and it's purely API driven. So even though there's a command line for talking to it, that command line is actually referencing an API that's inside the Kubernetes control nodes. And so it is structured with control nodes and worker nodes. So the control nodes host the API. They have all these little processes and containers that are constantly monitoring what's been declared in YAML files, somewhat similar to the Docker Compose one, but again, more complicated. And they're constantly making sure that what you've specified in those YAML files is real in the cluster. So if you say, I want 3 instances of my web front end and running in containers in the cluster, the controllers will make sure that that always happens. And if one of them dies, it'll start up another one and replace it. If one of the nodes, server nodes, the actual hardware nodes in your cluster dies, the Kubernetes controllers will move all those, will recreate all the containers that were on that dead node. It'll recreate them on other nodes and bring them all back up like nothing happened. So it's incredibly powerful. It takes all the years and decades from IT and development learning about things like availability and distributed systems and everything else, and bakes it all into this container management system. So massively powerful, but also, again, in order to dive into it, it would take a whole other presentation and hours of time. But it is part of the Cloud Native Computing Foundation trail map. That's what they call this, their trail map. So Kubernetes is actually just one small part of a very large and also complicated ecosystem that spans the entire development lifecycle, right? Everything from when you're first writing your code to when you're doing automated integration and deployment and testing, all the way through to deployment, orchestration, network, software-defined networking, the whole 9 yards. The trail map gives you kind of a look at all the bits and pieces that are sort of certified by the Cloud Native Computing Foundation. Almost all of these things that are on this chart actually have dozens of other alternative products as well that could be used or dropped in place of them. But the point is, this is what's making up Cloud Native Computing, Cloud Native development today. The thing that developers interact the most with is Kubernetes and container builds and things like that. But the environments that are being deployed into have all this other rich functionality, right? With observability, for example, if you look at item 4 over here, observability and analysis, right? So most Kubernetes, productized versions of Kubernetes, have incredible amounts of monitoring. They've got dashboards, and they've got all this observability and reports and monitoring that help DevOps, particularly the ops part of DevOps, make sure that everything's healthy and working the way it's supposed to, and monitoring it, things like that, right? Checking for security issues, whatever it may be. Orchestration and application definition. This is Kubernetes YAML files that I was referring to. There are higher level structures above those Kubernetes YAML files, like Helm and OpenShift's operators and things like that, that do even more to define exactly how this application is supposed to run, how to keep it exactly the way the original developer intended it to run, and so on. So this is a both wide and deep ecosystem, and even though I've spent a couple of years in this world already, I sure as heck don't know all of it. But it's exciting because it's a really new way of building applications. It very much complements agile development and DevOps in that it's the formalized way of a decomposed microservice-based system where you've got lots of little pieces and you can rapidly make lots of little changes that over time add up to massive change, right? So if you think about agile being short iterations of development where you bite off a little bit, you spend whatever your iteration cycle is, maybe it's 2 weeks, you spend 2 weeks making this small change, make sure it's perfect, testing it and getting it out into the world, and then spinning through that cycle again and again and again. This kind of environment is very conducive to that because everything is broken up into these small little services. So every time you make a change, you can control the scope, you can keep it small. The amount of testing you have to do is confined to the one thing you're changing, and everything else that talks to your container, generally speaking, is doing so through a defined message, or an API, or something like that. So you're free to make changes in features and code as long as you're maintaining your APIs in message formats. So, excuse me. So again, this is part of sort of modern cloud native application and service development, and it's a rich world. It's exciting. It's mind blowing. It's an overload every day trying to get my head around all of this stuff, but it's pretty incredible. Boom. Quick talk about DevOps. What is DevOps? So I was just kind of mentioning it in a way. It is this culture shift in the way we build things, and it's an extension of Agile. DevOps comes out of Agile. When you try and take what you do with Agile and expand it to not only writing software, but also managing, operating, deploying that software, the whole life cycle end to end, from the time you build something all the way through all the testing you do to when you deploy it out into the world, and then you get that feedback cycle going, and you're iterating and making rapid changes in production. It's hard for people to wrap their heads around sometimes, especially if you come from the old waterfall cycle, where you expect to spend months building new features and then eventually deploy them out to the world after they've been strenuously tested. And the first time anyone sees them is months after the developer actually made the change. In the DevOps world, the idea is that you do this in much tighter cycles. You make smaller changes, you test the heck out of them, you do as much automating as you can to automate testing, to automate integration and deployment testing, things like that, so that you can be really confident that every little change you make isn't going to break the world. And that allows you to make a whole bunch of little rapid changes instead of making massive monolithic changes all at once. Done properly, it supposedly gets features out into the field faster and accelerates development. As you can imagine, however, it's extremely difficult to get right. It is a culture shift. It does require diligence in places where you may not have had diligence before. And you do need all of these things in place. You need CI/CD, you need automation, you need continuous testing, continuous evaluation. When it comes to security, you need continuous scanning and things like that. But like I said, the new cloud native ecosystems are conducive to this, right? They're built heavily around automation. They're built around decomposed services that are very small bites to bite off. And so trying to bring Agile and DevOps into that kind of environment is much easier than if we were in a world where we had to stand up individual servers and tear them down and redeploy them every time we had a new version or something like that. Boom. And again, DevOps cycle. So this is a lot like, I think somebody's gonna do a presentation in a week or two on Agile. You will see at that time, this is very complementary with Agile. It's very similar in terms of the way you do iterations, you do continuous testing, and then you go through this plan, build, test and deploy, figure out what you did wrong, and rinse, wash, repeat. It's just, again, in DevOps, that's been extended out a little bit further now because it includes actual operations, right? It includes what happens after you deploy. And the team, the DevOps team, is integrated, right? So you don't just have separate development people and separate system administration people. They're all together in an integrated team. They're constantly communicating and feeding back through this kind of a loop. And that helps with the acceleration, right? Because again, in the old way of doing things, software development teams were in their own little ivory tower. Operations people were in their own little ivory tower. And there was, you hand a CD over the wall to the ops guys and say, here's the CD and a bunch of documentation to make it work. Now, there's no strict separation like that. Development and operations work very closely together in this whole cycle. So when you're doing your planning, before you get into development and everything else, you've got your DevOps people are at the table trying to tell you if you're crazy with what you're trying to do, and or figuring out how they're going to deploy safely the things you're building. And so this cycle can be really tight, and you can get rapid change. And at the end of the day, that's usually a good thing. And that's it for me. Okay. So again, like I said at the beginning, this is a lot of topics to try and cover in one session. So I've breezed through a lot of it, and I've done a lot of talking, which I don't like. I would rather be asked questions, but there wasn't much time. So any final thoughts or questions? Silence.
Rory, great
Yes, ma'am.
job as usual.
Well, maybe we'll do, we will break it up into bite-sized chunks next time. Like I said, it is exciting. It's intimidating like crazy to get into Kubernetes, but it's also pretty exciting when you see it working in production. The possibilities are remarkable. Obviously, Kubernetes is not going to work for everything. Not every single service in the world can be broken up into little pieces and still perform properly. But for a great deal of what we do today and the kind of applications we deploy, it's pretty amazing. Okay. We can call
That was
it there.
quite a bit of information. You did a good job condensing it.
Thank you.
Yeah, it's
It is
intimidating
a,
because we don't see we're used to like GUI.
yeah.
But here it seems like you need to know all the scripts and functions.
Yeah, and like I say, that seems kind of complicated at first, getting to learn and memorize new command line utilities and stuff like that. But the thing that's really amazing about it, whether it's something like Docker Compose or the command line for Kubernetes, is it's hiding an incredible amount of complexity and doing a lot of things for you. So even though command line may not be everyone's favorite, it provides fast access to a lot of power. So, and then, like I said, there are products like OpenShift, Red Hat's OpenShift, and some of the offerings from like the likes of AWS and Azure that do give you web interfaces to all this, and allow you to manage. You can manage Kubernetes cluster through OpenShift, basically with point and click if you want to.
Are they more resistant to virus, those hacking?
Not exactly. I mean, all the same issues exist. The nice thing about something like Kubernetes is it has defined ways of setting up networking and exposing ports and things like that. And it's all declared in the same sort of style, like with YAML. So when you set up a multi-container application in Kubernetes, for example, you can define exactly which ones are allowed to talk to each other and which ones aren't in a network policy. And again, that's in the YAML file that can be checked into a GitHub repository. And so it's easy to inspect, right? And it's visible to everyone, right? In the past, when again developers wrote their code and then they passed a CD and a documentation across the fence to the operations people, the developers had not necessarily any idea what the ops people were setting up for firewall rules and things like that. Whereas now everybody's got visibility on the whole stack, and everybody can take an interest in or view things like network policy, or which ports are exposed out to the world, where the certificates are, things like that. It's all declared in this configuration file in a source code repository. So security people can inspect it, network people can inspect it, and it's much more transparent end to end that way. So pluses and minuses, right? At the end of the day, if you're exposing something to the internet, for example, that code still has to be secure. Right? So the classic mistakes that developers make when building web applications are still a problem. So that hasn't gone away. But again, the transparency and visibility and observability is formalized and much more available. So that's good.
Okay, thanks.
Sure.
Thank you, Rory.
Sure thing.
Thank you, Rory.